All right. So we are here right now. We'll talk about the introduction to matrix algebra today. Um, you may ask, why do we need to learn matrix algebra, right? So you will never hand calculate any linear or matrix algebra in your life, but this is actually fundamentals to understand the multivariate statistics analysis. So without understanding some backgrounds of matrix algebra, you can't really deeply understand the multivariate statistics. So today I'm going to introduce this will be some high level introduction to matrix algebra. So let's talk about it. Okay, so right. So matrix algebra. So first, basics of a matrix. So in the last class, you learned about the covariance matrix, right? So this is kind of a pop quiz. So we have 4 graphs right here, and then I would say this is x1 axis, this is x2 axis, and this is x1 and x2 and x1 and x2. Okay. So can you guess which matrix, which covariance matrix explains this scatter plot? Matrix 1, 2, 3, 4. Which one?
3? I guess it's 3.
Do you all agree?
Is it 4?
4. Why 3?
Because x1 has a larger variance and there is no covariance between x1 and 2. So the diagonal should be 0 and 5 is larger variance indicating x1 there.
Yeah, it actually should be matrix 3 because, for example, in this case, let's say A, B, and C, because this is covariance, it should be same, right? So this is x1, x2. This is the degree to which x1 spreads out, right? Because this is an information about the variance of x1, right? Then this is the degree to which x2 is spreads out, right? Because this is variance of x2. And then this is covariance between x1 and x2. So in this case, you can see, we can see a lot of variations for x1. But if you look at the x2 axis, there is very small variations, right? So it should be 1. And there is no correlation between x1 and x2, so it should be 0 and 0. Does that make sense? So what about this case? The second graph. Number 4. So do you all agree? Yeah, it should be number 4, right? Yeah. 1, 0, 0, 5, right? Because if you look at the x-axis, the very small variance. If you look at the y, the very large variance, there is no relationship between x and y. So 0 and 0, right? What about this case? It's gone. Between A and B, matrix 1 and matrix 2.
1 or 2,
Matrix,
1, yeah.
Yeah, matrix 1, right? Why this is matrix 1?
It's positive.
Yeah, we can see some positive relationship, right? So if you look at this, the covariance is positive. But if you look at this is the covariance is negative. So this is matrix 1 and matrix 2, right? Okay. So all clear? So this is matrix algebra. Basically, this is matrix algebra. So this is covariance matrix, and covariance matrix can be plotted in the geometric space. Okay. So let's talk about the vector first. So what is vector? Right. So vector is one-dimensional matrix. Okay. Basically, the matrix vector has only one column or one row. So in this case, we have only one column, right? So 5, 3, 2. This is one-dimensional matrix. In this case, this is one column, right? This is vector. Okay. And if it transposed, we'll learn about the transpose pretty soon. But if it transposed, this will be the row vector. So this is a column vector, and this is a row vector. Okay. So let's look at this. So vector, actually vector is, a vector represents some direction, okay, in the geometric space. So for example, this vector is -2 and 3, right? This is a column vector. So which means, okay, -2, 1 and 2, right? And then go up. We come to the left and then go up 1, 2, 3, right? So this is origin point, and then this line. This is vector. Okay, so vector tells us some direction. Okay, what about this case? This is -2 and -1.5. So we go -2 and -1 and 0.5. So this is vector. Okay, so this vector matrix can be expressed like this in the geometric space. Okay, so this is vector. So how can you check vector in the R? So this is R syntax. So for example, vector C is combined. So this is a small c, it should be small c, and then you can type your vector element, then type it, and you can see the vector. And you can check if this is vector or not. Is that vector returns true? So this is vector, okay? So this is a simple R code. And then next, what is a matrix? So matrix is a rectangular array of elements arranged in rows and columns. So basically, matrix is an extension of a vector. So matrix can have row vector and column vector. So it has some dimension. Okay. So for example, in this case, how many rows we have? 2, right? 1 and 2, right? So number of rows are 2. And how many columns? We have 3 columns, 1, 2, 3. So this is 2 by 3 matrix. Right. So this is matrix. All the multivariate statistics, I mean, basically data set is matrix format, right? We have many different variables, x1, x2, x3, and x100. And we have many observations, right? ID1, ID2, ID3, and ID100. All data point is basically vector. I'm sorry, it's the matrix, right? So rather than using numbers, so we can present parts of the matrix as a symbol. So like in this case, we can put A11. The 1 means the first number represents row. The second number represents column. Okay, so which means this is A element in the first row and first column. And this is A element from the first row and second column, right? And a element in the first row and third column in this case, right? So for example, we can see this one. So matrix, and then we can say this is the 1, 2. This means first row and second column, right? 1, 2 is what? What is the answer? What element?
2.
2, right? So first row, right? First row and second column, 2. What about 3? No, I'm sorry. 2, 3.
6.
6. Second row and third column, 6, right? This is how we can represent the matrix, the elements. So it's easy. And then now we can talk about how can we make a matrix using R. So we can use matrix function. So matrix function, and then you can put the data, right? And then this is vector, this is numeric vector. I put this 1, 2, 3, 4, 5, 6. These are all the elements, right? And then you can specify the number of columns and number of rows. So number of rows and number of columns, 2, 3. So which means I'm going to create a 2 by 3 matrix, right? And then I put by row equals true. So which means I'm going to assign each element and the by row. Okay, so which means 1, 2, 3, 4, 5, 6. So in R, actually false is default. So if you don't put anything here, it will assign 1, 2, 3, 4, 5, 6. Okay. It will assign column wise. But if you put the by row equals true, it will assign numbers in the row wise. Okay. And then we can check this is a matrix using the class function. Okay, it's easy, right? So far so good. Good. Right. Next, let's talk about the transpose. Transpose is you can interchange the rows and columns of a matrix or vector. So you can shift, right? So the first row we go to the first column, and second row we go to the second column. This is transpose. Okay, so this is transpose. So for example, 1, 2, 3, we have one column vector. If I transpose, it will be 1, 2, 3. It will be row vector. Okay, so this is transpose. And then we use this symbol for the transpose, so which is called prime. In matrix algebra, so when we transpose, we put this prime, or we put like transpose T. Okay, they're same. If you see this sign, that means okay, we will transpose a matrix. Or if you see this prime, which means we will transpose a matrix. Okay. Okay, this is transpose, and you can transpose your matrix using R very easily using T transpose function. If you put T, and it will transpose. Okay, so first row comes to the first column, the second row comes to the second column. Right? Okay. And next. Okay, now let's talk about the matrix addition and subtraction. You can add or subtract, multiply, divide, division for the matrix algebra. So all the matrices. So let's say we have two matrices. Okay, so these two matrices is a 2 by 3 matrices, right? And then if we add these two matrices, so basically the addition and subtraction is based on the element by element. So which means we will add first element and second element. 1 minus 1 is 0. And 2 plus 10 is 12. 3 plus minus 1 is 2. And 4 plus 5 is 9. And do the same thing, 10 and 14, right? This is the matrix addition. And the subtraction is the same. It should be the element by element. So 1 minus 1 is 2. And 2 minus 10 is minus 8. And 3 minus 1 is 4, right? Do the same thing. You can get these matrices. And matrix addition and subtractions are distributive, which means if you transpose the sum of two matrices or sum of two matrices or subtraction of two matrices, so you can get this relationship. So A plus B, and if you transpose, it is the same as A transpose plus B transpose. Or A minus B matrix and transpose, it is A transpose minus B transpose. Also, this relationship is satisfied, so you can get A plus B plus C matrices. Okay, this is the basic, the characteristics of a matrix. So if you look at this, we created two matrices. Here is the A matrix, and here is a B matrix, right? And if I A plus B, if I add these two matrices, so 1 minus 1, right? 0. And 2, 10 is 12. And 3 minus 1 is 2. It's the same. And the A minus B is the same. 1 minus 1 is 2. The 2 minus 10 is minus 8. Just same. Okay. Now I'm going to show you how A plus B transpose equal to A transpose plus B transpose. Let's look at this. So we did a transpose A plus B matrix, and then you will get this result. So I'll do this for you. And then if you transpose A plus transpose B, you still get the same result, right? So you can verify the using R. And also, this is A minus B matrix and then transpose, and you will get this result. And also transpose A minus transpose B, they're same. Okay. They're same results. Okay, and then scalar. Scalar is a matrix with one row and one column. Actually, scalar is a single number. Okay. So if you look at this, let's say A matrix is A11, A12, A13, and A21, A22, and A23. If I multiply C, this is a single number, right? And the C will be multiplied for each element. So like this, right? So this C is a single number. So this is scalar. So for example, this is our matrix, and then we multiply 2, and this is 2A, right? And it will be 2, 4, 6, 8, 10, 12. This is the scalar. Okay. Basically, what scale does is it is a scaling factor. So basically, what matrix does is matrix is a linear transformation. Okay. For example, if you have a one vector, okay, this is vector, and then if you multiply matrix, it will have another vector. Okay. So matrix, what does matrix do is it is actually the linear transformation. We'll see that. Okay. So vector scale looks like this. Okay, this is, what is this? This is a 3, 1 vector, right? 1, 2, 3, and 1, right? So this vector is 3, 1 vector, right? And then if I multiply 2, and then now we have 6, 2 vector, right? 1, 2, 3, 4, 5, 6, and 1, 2. So we have 2. So this vector is V. I would say V like this. And this is 2 times V, right? So a scalar doesn't change the, it doesn't change, I mean, it still remains direction, right? Or, no, I'm sorry. But it can change the direction. If I magnitude a negative number, it will goes to this way. Or also it increase the magnitude of your vector, right? So if right here, the scalar, this is increase magnitude of your vector, or sometimes it changes direction of vector. Okay. So scalar is the scaling factor. So how can we scale? How can it, you know, the changes our vector space? So this is scalar. And now let's talk about the matrix multiplication. So suppose you want to multiply matrix A and matrix B. So matrix A times matrix B, it is AB, matrix AB, okay? So in order to do this, you need the number of columns of A to be same as the number of rows of B matrix. So what that means is, let's say A matrix is 2 times 3, and B matrix is 3 times 10, right? So the column of the first matrix should be, number of columns of the first matrix should be same as the row of the second matrix. Okay, 2 times 3 and 3 times 10, they're same. So it will be 2 times 10 matrix. Okay, what about this case? 2 times 3, and I'm sorry, 3 times 2 and 1 times 4. Can we compute this matrix? No, because they are different, right? So 2 and 1 is different. So we cannot compute matrix. So matrix multiplication will not be possible in this case. So always this Z and Z, right? So they should be same. Okay. So and then one more important things is here. So this is a matrix multiplication and A and B. So let's say this is A matrix and this is B matrix. So A matrix is, this is 1, 2, and this is 2 by 3, right? And B matrix is what? This is 3 by 2, right? So 3, 3, we're same. They're same. So we will get this 2 by 2 matrix. Okay. So and then how can we compute the matrix multiplication? This is A1 times B1 here, plus the second element of the first row, A12 times B21, and this one times this one. This is the first element of the 2 by 2 matrix. And then let me change my color. Then A1 times B12, A12 times B22, A13 times B32. This is the second element. And then third, let me change the A21 times the B11 and A22 times the B21 and A23 times the B31. So this is third element, and the last element should be, right, what color should I use? So A21, B12, A22 times B22, and A23 times B32. So this is the third, fourth. So in that way, we can compute the matrix algebra, right? Any questions here? No. So in R, if you want to do a matrix algebra, you have to put like this. This is for the matrix multiplication, okay? This this will do this calculation, but if you just put 1, okay, this means it will multiply element by element. For example, A is 1, 2, 3, 4, and B is 1, 1, 1, 1. So if you put like this in R, what does this is 1 times 1, 1. 2 times 1 is 2. 3 times 1 is 3. 4 times 1 is 4. Okay, so this A times B in R, if you want to do a matrix multiplication, you have to put this one. Okay, so here is the example. So this is A matrix and this is a B matrix, right? So A times B is 1 times 3, 2 times 1, 3 times 0. Right here, this is 5. And 1 times 0 plus 2 times 2 plus 3 times 1 is right here. This is 7. And 4 times 3 plus 5 times 1 plus 6 times 0 is right here. That is 17. And 4 times 0, 5 times 2, and 6 times 1 is 16. Okay. It's okay? Any questions so far?
So we need to be very literal because it's not communicative. Like B times A and A times B are not equivalent.
Yeah,
So
not
in our
equivalent.
assignments, we need to make sure.
Okay, so yeah, but actually I'm going to show you later, but I will show you. So A times B is not equal to B times A here, because, think about this one. 3, 0, 1, okay, B times 1. Let's think. B is, what is it? This is the 3 by 2 matrix, right? And A is 2 by 3 matrix. So 2, 2. So it will show us the 3 by 3 matrix. A times B is 2 by 2 matrix, right? But B times A is 3 by 3 matrix. So A times B and B times A, they're different. So let's do that. So 3, 0, 1, 2, 1, 0 times 1, 2, 3, 4, 5, 6. Okay. So it will be 3 times 1, right? 3 times 1 plus 0 times 4. And 3 times 2 plus 0 times 5. And 3 times 3 and 0 times 6. Oh, plus 0 times 6. In the same way, you can do 1 times 1, right? And 2 times 4. 1 times 1 plus 2 times 4. And 1 times 2 plus 2 times 5. Oops, what is that? Oh, come on. Okay. So 2 times 5. And what else? 1 times 3 plus is 2 times 6. 1 times 3 plus 2 times 6. And 0 times 1, is that correct? 0 times 3, and oh, I'm sorry, 0 times 1, confusing, plus 1 times 4, and 0 times 2, oh my gosh, 1 times 5, and 0 times 3 plus 1 times 6. In that way, we have 3 by 3 matrices. So they are not equal. So A times B is not equal to B times A. Okay. Is that clear? Right. So now as you can see here, so the order of multiplication must be specified. And multiplication is distributive over addition and subtraction. So this relationship can be satisfied. So A times B plus C matrix is A times B and A times C. Or A times B minus C is A times B minus A times C. And this is AC and BC and AC and BC. Okay. These relationships, okay. And then also, if you transpose AB matrix, let's say, there will be B transpose and A transpose. Okay, so this is not equal. In the multiplication, we already see if you transpose A plus B matrix, this is satisfied, but this is not satisfied. So when you transpose multiplication, the order will be switched. So A times B, and this is a B transpose and A transpose. Okay. Right, now you can see here. So I created A matrix. This is A matrix. And I created another B matrix. This is a B matrix. Okay, so this is 3 by 2 and 2 by 3. So it will return, what is that? Oh, I'm sorry. This is 2 by 3. This is 3 by 2, right? So, and then this is A times B. In R, you have to use this sign. Percent and percent. So which means A times B, and right here. So it will return 2 by 2 matrix, but B times A is 3 times 3 matrix. Okay. So A times B is not equal to B times A. Okay. I posted R syntax on the Blackboard. You can play it yourself. Okay. Right now, linear systems, any linear relationships that can be expressed in the matrix format. So for example, this is the linear function, right? X, Y, Z. And this is another linear function, right? So these three regression line can be expressed like this. So 2, 5, 3, and 4, 0, 8, 1, 3, 0 is right here. So we can make a matrix here. And then X, Y, Z, this is a vector, column vector. Okay. And then now we will get this result. It's right here. Okay. So based on this relationship, you can see this is a vector, right? If we do the linear transformation, so this is a matrix. If we do the linear using this vector, if we do the linear transformation by multiplying matrix, we will get another vector, right? So which means if let's say we have some vector. If we multiply some matrix, we will get another vector. Okay, so basically the matrix does linear transformation. Okay, this is very important concepts to understand eigenvector and eigenvalue. Okay, we'll talk about eigenvector and eigenvalue later. So remember, if we linear transform the vector using some matrix, it will be another vector. Okay. Right. So now let's talk about the symmetric matrix. So this is a symmetric matrix. If A is equal to A transpose, that is called the symmetric matrix. So this is A matrix. If we transpose this one, so think about this. First column goes to the first row, and second column goes to the second row. After transform, right? After transposing, A is still equal to the A prime, right? So this is a symmetric matrix. This is called the symmetric matrix. Okay, and then diagonal matrix is this variance. Actually, the variance, sum of a variance, right? In the covariance matrix, these are all variances, right? So these diagonal, sum of diagonal, I'm sorry, that is actually trace, but so these are A1, 2, 3. We only have the diagonal elements, and off diagonals are all 0. This is called diagonal matrix. Okay. So forget about this one here. This is diagonal matrix. And identity matrix is, this is a special case of a diagonal matrix, but identity matrix always have 1 in the diagonal element. This is identity matrix. Okay. So identity matrix is noted by the I. So if you multiply any matrix by identity matrix, will be same matrix. So for example, A matrix times identity matrix is A. Okay, so in this example, this is A matrix and this is I matrix, right? A times I, you still get A, because look at this. 3 times 1 is 3, right? And then 3 times 1 and plus 1 times 0 is a 0, and 2 times 0 is a 0. What about this case? 3 times 0 is 3 times 0 plus 1 times 1 plus 1 times 0. 0, 0, 0, 0, right? This is a 3, this is 1. And also if you do the 3 times 0 plus 1 times 0 plus 2 times 1 is 2. So it's still 3, 1, 2, right? It's 3, 1, 2. So if you multiply any matrix by identity matrix, returns itself. Okay, this is identity matrix. Any questions? No? Right, and linear dependent. So the linear dependent means in the matrix, the one column is linearly related to other column, which is called the linear dependent. Okay, for example, in this case, we have 3 columns, right? 1, 2, 3. So let's say this is one is x1, x2, and x3. So if you look at this, so x2 and x3 are linearly dependent, because if you look at this, these 2 columns satisfy this relationship. If you multiply 3, to the second column, you will get third element, right? So the one element and the one column is determined by another column, right? Their relationship is related to each other. So this is called linearly dependent, okay? So this means the columns of A are linearly dependent. So A2 and A3 are linearly dependent, right? So a set of column vectors are linearly dependent if there exist constants, the lambda 1 through lambda c. In this case, look at this. But if lambda 1, 2, 3, if they are all 0, in that case, they are linearly independent. Okay. And then rank is rank of a matrix is maximum number of linearly dependent columns. Okay. So how many columns are linearly dependent in this case? In this example, how many columns are linearly dependent? Any answer? X2 and X3, right? X2 and X3 are linearly dependent, right? The rank equals A is 2. Okay. The rank returns the maximum number of linearly dependent columns. Okay. For example, let's say 0, 1, 0, and 1, 1, 1, 2, 2, 2, and 3, 3, 3. Okay. In this case, so X1, X2, X3, and X4. And X2, X3, and X4, they are linearly dependent, right? If you multiply 2, you will get this one. If you multiply 1 times, I'm sorry, it should be 4. It's fine, 3. 1 is linearly dependent, right? So how many variables are linearly dependent? If in this case, X2, 3, so it will give us the 3 rank. Okay, the rank is the maximum number of linearly independent. I'm sorry, this is linearly dependent columns. Okay. All right, so I will skip this one. And then inverse of a matrix is if a matrix is B, inverse is -1. This is 1 over B, right? So 3 inverse. This is 1 over 3, right? So this is inverse relationship. And the inverse of A is A to the -1. And then A times A inverse, this is equal to A inverse times A matrix. And this is identical matrix. Okay. This is identical matrix. And then how can we find the inverse matrix? So this is the formula. So A is A1. So basically, let's say A is A, B, C, D. So A inverse is A times B, A times D minus B times C over. And then we switch these two. So D, A, and minus B minus C. This is the formula for the inverse matrix. Okay. So B matrix times B inverse is what? What is the answer? Any answer? Identity matrix, right? Identity matrix. So any matrix, if you multiply any matrix by inverse matrix, it is the identity matrix. All right, so here, this is an example. So this is A matrix, and if you calculate it, you will find this A inverse matrix. And if you multiply A times A matrix, you can check it. If you compute it, you will get this one. This is identity matrix, right? So off diagonal is 0, but diagonal element is 1. So I, right? So using RL, so you can create the matrix right here using matrix, data, and row and column by row function, and then solve. This is for inverse. Okay. If you want to get inverse, you can use a solve function. It's right here. And then A times A matrix times A inverse will gives us this value, but there are some the rounding errors, so I just put the round, so it will return the identity matrix. Okay. Right. So now recall. The matrix algebra, metrics can be applied to any other statistical models. So you already learned about the linear regression model, right? So we can compute the coefficients using matrix algebra as well. So I'm going to show you. So let's say we have this multiple linear regression, right? Y is our dependent variable, the beta is our independent variable, and we have a K independent variable, right? Beta 0 is intercept, I'm sorry. So we can explain like this. This is Y vector, right? And then we can have some data vectors. So this is, we have x1 through xk. So x1 through xk. So all the elements are here. And then I added x0 because this is the intercept. Okay, so this is actually 1, 1, 1, 1, 1, 1, 1. So first is intercept. So right here, intercept. Okay, because actually this is x0, beta 0 times x0, but x0 is 1. Right, this is intercept. So they are all intercept. And then beta, this is coefficient. Now we have the different coefficients right here. So beta 0, beta 1, beta 2 to the beta k. So right here, we have coefficient vector, and then we have some error vector, right? So all these relationships that can be explained by this matrix format. Okay. And then this matrix, this linear model can be explained by Y vector is equal to X matrix times Y vector plus some error vector, right? So look at this. This is matrix, right? X matrix. This is Y vector. This is a beta vector. This is the error vector, right? So Y vector, this relationship is Y vector is here, M times 1 is equal to X matrix. The first is intercept. And actually this should be 1. And then we have all the different data. And that this is beta vector, and this is error. And then if you run regression model, the URL or statistical package will estimate this beta coefficient for you, right? It will return the intercept and slope, right? So we can compute these relationships. We can still compute the beta matrix using matrix algebra right here. So here, like I said, this is Y is equal to X times beta plus E error. But for the computation, we don't we ignore the error. So this is Y is equal to X times beta, right? So I'm going to show you. You don't have to memorize this one, but if you multiply X transpose times X, X transpose times X, I just multiply same thing here, right? The relationship will not be changed, right? Because I multiply same thing, left and right. Is that correct? And then I divide by this relationship. Okay. So these two things are same, right? So it will be 1, right? So this will be, so this will be beta. So this beta is a coefficient matrix, a coefficient vector, right? So this is xtx, this is inverse, right? Do you follow this relationship? 1/2 is 2 inverse, the same thing. So this part is right here. So I would say this is xtx inverse times x transpose y is a beta. So this is right here. Okay, this is what we know. This is what we want to estimate, the beta coefficient vector. And we already have an x matrix. We already have a y, right? Then we can estimate this one. Any questions? So I'm going to show you. So using R. So here are, let's say we have a high school GPA and college GPA. We want to predict college GPA using high school GPA. Okay, and this is a high school. This is a high school GPA. This is a college GPA. So college GPA is our dependent variable, and high school GPA is our independent variable. And then I put 1 here because 1 is intercept. They're all intercept. And then using this matrix, I'm going to try to estimate the intercept and slope. Okay, so here is our high school GPA matrix vector, and this is college GPA. I posted R syntax on the Blackboard that you can play yourself. And then I combined this vector and 1 because 1 is intercept. So it will returns this matrix. And the college GPA is this matrix. And then let's find this one. And then let's find the beta. So this is what? This is the X transpose, right? And times what? X. And then solve, this is inverse. And then this is transpose X times Y. It's right here. So I computed it. If you run it, you will get this, the beta vector. Okay, so this is beta 0 and this is beta 1. So this is intercept and this is slope. Okay, so college GPA is equal to 0.707 plus 0.6996 times high school GPA. We can get this relationship using matrix algebra. Okay. So I'm gonna compare. This is what we get, right? So you learned this one, right? The LM function in the regression class. If you run it, you will get the same result. Intercept is 0.707, 0.707, and a high school GPA 0.669, 0.669. Right. So, so matrix algebra can be still applied to any other analysis to get the coefficient. So all these matrix algebras are applied to the structural equation modeling, exploratory fact analysis, confirmatory fact analysis, multi-level analysis, right? So they're all doing these kind of the matrix algebra to get the coefficient. Okay, now let's talk about the trace. Trace is just simple. Trace is all the sum of diagonal element. That is trace. Okay, so trace is the sum of diagonal matrix. Think about the covariance matrix. So 2, 1, 3. Okay, let's say this is covariance matrix for A. So trace of A, this is what? This is sum of variance, right? The sum of variance is the trace in the covariance matrix. So these variance and covariance information are really important in the PCA or exploratory fact analysis. We'll more talk about that one, but you need to understand this relationship. Questions here? No? Okay, now let's use R to get this is A matrix. And then how can we get the trace? First, we will get the diagonal using diagonal function. If you use diagonal, it will return diagonal element 1 and 4, 1 and 4, right? And then I added a sum. So we will sum these two values, these 5. So 1 plus 4 is 5. So that is a trace of A is 5. Okay, this is trace. And now determinant. Oh my gosh, what is determinant? Determinant is the volume or area of a matrix. Okay, so let's look at this 2 by 2 matrix. 2 by 2 matrix is determinant is this one times this one minus this one times this one is determinant of this matrix. For example, A, B, C, D is AD minus BC. This is determinant of A matrix. Okay, so determinant is if your matrix is only 2 dimension, that will produce area. But if you have more than 3 dimension, that will produce the volume. Okay, if your matrix only 2 dimension, it will be area. But if you have a 3 dimension, more than 3 dimension, it will be volume. So what is determinant? Let me show you. So here's some more example. Let's think about this. This is matrix, right? So 3, 0, and 0, 2 matrix. So this is the first column vector, second column vector. So first column vector is the 3, 0, right? So here, 1, 2, 3. What is this? Sorry. So this is first column vector, right? And the second column vector is 0, 2. So 0 and 1, 2. So this is second column vector, right? So first column vector, second column vector, it will make some area. So geometrically, this is a matrix. So what is this area? 3 times 2, right? 6 is, this is determinant. Okay. What about this case? Think about this. 1, 0, 1, 1. And first column vector is 1 and 0. So this is the first column vector. And the second column vector is 1 and 1, right? So this is second column vector. So these two vector will make this matrix. This area is a 1 times 1. 1. Right? This is area. This is determinant. So look at this. So based on our formula, A, B, C, D, determinant was AD minus BC. So 1 times 1 minus 1 times 0 is 1. Right? So in this case, 3 times 2 minus 0 times 0 is 6. So it is our area. Okay. And one more example. And 3, 0, and 2, 2, and 1, 2, 3, and 0. There is no y. So this is the first column vector. And second column vector is 1, 2, 1, 1. This is second column vector, right? And so you can make some this kind of the matrix. What is area of this matrix? So it's 1, 2, 3. 3 times 1, 2. 3 times 2 is 6. This is determinant of this matrix. Okay. And one more thing, determinant. This is important because this concept is applied to the eigenvector and eigenvalue later. So if you look at this, in this case, we have a 4, 2 vector, 1, 2, 3, 4, and 1, 2. We have this vector, right? And then we have another 2, 1. So 1, 2, and 1, 2, 1 is right here. This is another vector, right? These two vectors on the same line, right? Do you follow me? Yes, please nod your head. Okay, so if these two vectors on the same line, what is the area? 0.
0.
Yeah, 0. Yes, 0. So this is if two vectors on the same line, the area will be 0. So determinant of this matrix will be 0. Okay, so we will use this concept later. Okay. Okay, so now and here, so this is determinant code R. It's very easy. You know, you can very easily compute the determinant, but more important thing is to understand what is determinant. Okay, right. So also determinant can be negative value, but like I said, determinant is area or the volume, but how can it be negative? But usually we evaluate the determinant as absolute value. But if direction, in this case, this goes 1 and 1. I'm sorry, let me change my color. 1 and 1 is right here. But this case, 2 and minus 1, 1, 2, and minus 1 goes this way. So if direction is negative, it can have a negative determinant. Okay, so determinant can be positive or negative, but it can be interpreted as area or volume of your graph or your matrix. I'm showing only 2 dimension because if I add one more column or one more row, this will be 3 dimension, right? It's hard to draw. So and then we cannot draw 4 dimension, right? So I'm going to show you only 2 dimension case here. And then last topic, eigenvalue and eigenvector. So if you already took psychometrics, you already learn about the eigenvalue and eigenvector, right? The EFA, right? What is the rule of thumb to extract factor? If your eigenvector eigenvalue is greater than 1.0, you extract factor, right? So what the eigenvalue means. Right. So eigenvalue and eigenvector. So these two concepts are really important to understand the PCA and EFA. And also it is very widely used other multivariate statistics. So here, for the transformation matrix A, like I said, let's say we have some vector X, okay? And we have some matrix, okay? So I already, like I said, matrix does transformation, linear transformation, right? So which means, okay, if we transform this vector using this matrix, and it will return some vector, right? Some vector, but it will be linearly dependent. So for example, in this case, this is vector X, right? And this is matrix. Okay, we have some vector, but if we multiply some matrix, that means if we linearly transform this vector, it will get another vector. But this vector is linearly dependent in this case. If you 8 times x, we will get 3x, right? X is 1, 1. Your new vector is 3, 3. Can you see here? 1, 1, and 3, 3. So this can be 3 times 1, 1, right? So this relationship satisfies 8 times x is lambda times x. So this is eigenvalue, and this vector is called eigenvector. So I found a really, really good graph. Oh, again, one more step. Let's say we have some vector. If you multiply some matrix, that means it is a transformation, linear transform form, and it will return another vector format. Okay, you understand this relationship, right? Okay, I'm gonna show you a graph here. I found a really nice, oops. This is Korean website, but I think that this is really helpful. Okay. Oh. Okay. So this x, blue x is our some vector. Okay. And then we multiply a. So this orange line is a linear transformed vector after multiplying x. Okay. So if we multiply x, this graph will be this one. Okay. So if I multiply any other, I can multiply all possible vector here. So look at this. You can see here, right? And then at some point, these two vectors will be overlap. Oops, I'm sorry. Okay, like this, right? So in that case, 8 times x is equal to some constant times x. Does that make sense? So that constant is called eigenvalue. And this vector satisfying this relationship is called eigenvector. Okay, so let me go away. Okay, so this way, this way, this way. I multiply all different vector, and then at some point, I have another overlap, right? So I can have another eigenvector, right? So in this case, how many eigenvector you can have? 2, right? So 1 and this lambda, so 8 times x is equal to some constant times x, right? So that constant is called the lambda, and that is eigenvalue. And then, okay, go. Oops, I'm sorry. And again here, okay, another eigenvalue and another eigenvector. Okay, this is eigenvalue and eigenvector. So here, this is x is, and if we this is original vector, and then after transform by multiplying a matrix, it will be like this. Okay, and these two original vector and transformed vectors on the same line, and that is eigenvalue, and this x is eigenvector. Okay, so why eigenvalue and eigenvector matters? Because eigenvector produced a maximum variance of the axis. So I mean, I will more talk about it in the PCA and EFA session. Okay, but this is really important to understand the concept here. Okay, so what is eigenvector, and how these two vectors are related to each other? Okay, eigenvector and eigenvalue. Okay, so briefly talk about it. So x1 and x2, we have different data set like this. Okay, and how many variables we have? X1 and x2, right? And then let's say we want to reduce the dimension. Okay, we want to reduce, and we have a 2 dimension, but let's say we want to reduce the dimension, make a 1 dimension, right? We need to find some axis. So in that case, probably we can try, I mean, you can draw any line like this, and then you project all the values here. Okay, I'm sorry. Or you can project like this. Okay. So if this is a PC1, if this is a PC2, if you project these data points to this line, the variance of this data set is this much, right? But if you project these data points to this axis, this will be like this, right? So PC1, this first axis that has much variance than PC2, right? So how can we find the best fitting line? We can use eigenvector and eigenvalue. Okay, so eigenvector always produce the best fitting line. So I will show you later. Okay, so eigenvector, eigenvalues of those are very, very important concepts in EFA and CFA, even the PCA. Okay, so I think I will stop here, and then we'll finish this one in the next class. And then I will introduce maximum likelihood estimation. So maximum likelihood estimation is one of the most commonly used estimator in multivariate statistics. So maximum likelihood estimation is very efficient in missing data analysis and also all different types of analysis. So I will introduce the basic concepts of a maximum likelihood estimation, and then we'll talk about the missing data analysis. Okay. Any questions? Was it too difficult or is it okay? It's good? It was okay? Okay. All right. So Let me see the syllabus one more time. The first assignment will be out on February 11th, and the first quiz will be out on February 9th. Okay, so in the next class, I will more talk about the assignment and the quiz. Okay, so I will post a recorded video on the YouTube. So if you want to watch again, feel free to watch and email me if you have any questions. All right, I will see you next week. Have a good day.
Bye.
Bye.
Thanks, Phil.
Thanks.
Phil. Sorry.
Hey, okay?
Yeah. I got one question actually.
Sure.
Yeah, it's about linearly dependent. Is that only for column or it
Yeah,
works for rows too?
Only for columns.
Only for columns.
Only
So
for
is
columns.
is there any type of linearly dependent for rows? And I mean any names of it?
Because in the data analysis,
Mhm.
multivariate statistics, we assume that each individuals are independent,
Mhm.
right? Because row in the data set, in the row is each individual,
Oh, okay.
and the column is each variable.
Column. All right. Okay.
Do you understand what I'm saying?
Yeah.
Yeah. Okay. So column is a variable. So for
Mhm.
example, cognitive ability score, job performance score, or personality score, and then row is first people, second people, and third people. But in the most statistical analysis, we assume each individuals are independent.
Okay.
My score is independent with your score, right? Because if I copy your answer, probably
that would be dependent.
yeah, our scores will be dependent. But in statistic analysis, we assume they are independent.
Also, for columns, it represents variables,
Yep.
and for rows, it represents individuals.
Individuals, right? In the
Okay.
data set.
Okay.
All right, awesome.
Okay.
Is
Thank you.
And so far, is it doable, or was too difficult?
Yeah.
It's doable.
It was okay. I mean, yeah. The Korean site. The Korean site, yeah. That really helps for eigenvalues.
And eigenvector.
Yeah.
Okay. Good.
And if we find eigenfactor and eigenvalues, so if we find that, the two line will be linearly dependent, right?
Right.
Yeah, because they would. Just the magnitude, right?
Right.
Okay. Okay, got it.
Okay. All right.
Yeah.
See you later.
Okay,
Bye.
thank you.
Bye.
Bye.